In this video lecture, we will discuss the main features of real voltage and current sources and, more briefly, of controlled voltage and current sources. We have already met ideal voltage sources, and we know that an ideal voltage source is a device capable of maintaining some voltage across a load independent of the current required by the load itself. Let's assume that this load is a resistor with a resistance RL. In this case, if the voltage source generates a constant voltage E, then the current flowing through the resistor RL will be, by Ohm's law, E divided by RL. The voltage current trans characteristic of this ideal voltage source will be a constant one equal to E independent of the value of the current provided by the voltage source itself. In the case of a real voltage source E, if we measure the open circuit voltage at the output terminals of the source, we will actually find a voltage E. If we instead connect a load to the voltage source, we will find that the voltage across the load is not E, but will take a value E prime smaller than E. On the other hand, the current IL flowing through the load, if the load is a resistor, will be E prime divided by RL. In general, in the case of a real voltage source, the larger the current that the load requires, the smaller the voltage that the voltage source can provide. Therefore, when the current is zero, so in open circuit conditions, the voltage provided by the real voltage source is the same as the one provided by the ideal voltage source. Then, as the current required by the load increases, the voltage provided by the voltage source starts decreasing, going to zero as the current goes to infinity. We can also think of representing the voltage generated by the two voltage sources, so the ideal and the real voltage source, as a function of the resistive load attached to the source. Note that as the resistance goes to zero, the current flowing to the resistance goes to infinity. And as the resistance goes to infinity, the current goes to zero. Of course, in the case of the ideal voltage source, the characteristic of the source does not change and will be constant and equal to E for any value of the resistance. In the case of the real voltage source, the voltage provided by the source will be equal or very close to the voltage provided by the ideal voltage source for very large values of the load resistance, where the current gets close to zero. As the resistance value approaches zero, then the current starts increasing and tends to infinity. So the voltage provided by the real voltage source will tend to zero. The behavior we have just described for the real voltage source accounts for the fact that no real device is capable of providing an infinite power. Recall that the power provided by a voltage source is given by the voltage forced by the voltage source times the current that the voltage source has to provide to the load. This means that in the case of the ideal voltage source, as the resistor RL approaches zero, the power provided by the voltage source goes to infinity. On the other hand, the power dissipated in the resistor can be written as the voltage across the resistor squared divided by the resistance, which also goes to infinity as RL goes to zero. In general, a real voltage source is represented by means of an ideal voltage source in series with a resistor. The subscript S in RS is for series. The resistor Rs in the real voltage source serves the purpose of modeling the behavior described by the yellow curve in the plot. Let us verify that this model can actually reproduce that behavior. Let us call E prime the voltage between the two output nodes of the real voltage source. In case we connect no load at the output of the voltage source, E prime will be equal to E. So the open circuit voltage at the output of the real voltage source is exactly the voltage provided by the ideal voltage source in the model. What happens is that if we connect a resistive load, RL, at the output of the voltage source, you should be able to recognize by now that the circuit we have obtained is a voltage divider consisting of a voltage source E and two resistors RS and RL. So the voltage E prime across the output load RL is given by E times the loading resistor RL divided by RS plus RL. Of course, here, if RL goes to infinity, we get back to the open circuit case, and the voltage E prime becomes equal to E, the voltage provided by the ideal voltage source. More generally, if RL is much larger than the series resistance of the real voltage source, then E prime will be more or less equal to E. Note that if IL is the current provided by the voltage source to the load, then the voltage E prime can be written as E minus the voltage drop across the resistor Rs, which by Ohm's law is given by Rs times IL. This result shows that the voltage across the resistive load RL, which is the voltage provided by the real voltage source, depends on the current provided by the voltage source to the load and decreases as the current increases. So the model proposed for the real voltage source is actually capable of reproducing the behavior described by the yellow curve in the plot. The resistor Rs in the real voltage source is also called the output resistance of the voltage source. Based on the results we have obtained in the case of the real voltage source, we can say that a voltage source prefers an open circuit because in that case the current it has to provide is zero. And then it can maintain at its output a voltage which is as close as possible to the ideal case. On the other hand, a voltage source does not like to work with a short circuit as a load because in that case the current to be provided as well as the power would approach infinity. Note that in this equation, for Rs going to 0, E prime goes to E. Actually, when Rs goes to 0, the real voltage source becomes an ideal voltage source. We already know that an ideal current source is a device capable of forcing a given current into a load independent of the voltage across the load itself. Let's assume now that this load is a resistor featuring a resistance RL. In this case, if the current force through the resistive load IL is equal to A, then the voltage across the same load by means of Ohm's law will be VL equal to A times RL. If we assume for the sake of simplicity that the ideal current source we are considering generates a constant current A, then the current voltage trans characteristic of the source will have a constant value equal to A, whatever the value of the voltage across the load is. In the case of a real current source A, if we measure the short circuit current between the output terminals of the source, we will actually find a current equal to A. If we instead connect a load, a resistive one, at the output of the real current source, we will find out that the current flowing through the load is not A, but will have a value A prime smaller than A. On the other hand, the voltage across the load, VL, will be equal, again by Ohm's law, to A prime times RL. In general, for a real current source, the larger the voltage across the load, the smaller the current that the current source can force into the load. So, when the voltage across the load is zero, which corresponds to short circuit condition, the current forced by the real source into the load is equal to A, as in the case of the ideal current source. Then, as the voltage across the load starts increasing, the current forced into the load by the real current source starts decreasing, going to zero as VL goes to infinity. As we did for the ideal and real voltage sources, we can represent the current provided by the real and ideal current sources as a function of the resistive load RL. Note that as the resistance goes to infinity, the voltage across the resistance also goes to infinity, while for the resistance going to zero, the voltage also goes to zero. In the case of the ideal current source, the characteristic remains the same, so it will be represented by a constant current with value A for any value of the resistance RL. In the case of the real current source, the value of the current will be very close to the current generated by the ideal current source for small values of the resistance RL, and then will decrease as the resistance increases. As we have already said, in the case of the real voltage source, also in the case of the real current source, the behavior we have just described accounts for the fact that no real device is capable of providing an infinite power. We actually know that the power provided by the current source is given by the current forced into the load times the voltage across the load. The same power can be expressed in the case of the power dissipation in a resistor as A squared times RL, which of course goes to infinity if A is constant and RL goes to infinity. In general, a real current source is represented by means of an ideal current source in parallel with a resistor. The subscript P in Rp stands of course for parallel. The resistor Rp included in the real current source has the purpose of modeling the behavior described by the yellow curve in the plot. We will verify now that this model can actually reproduce this behavior. Let us call A prime the current flowing out of the upper terminal of the real current source. If we connect the two output terminals of the source with an ideal conductor, so if we short circuit them, then the current A prime will be exactly equal to A, which is the current provided by the ideal current source in the real current source model. Let's see what happens instead if we connect a resistive load at the output of the current source. The circuit we have got here is a current divider consisting of the current source A and the two resistors in parallel, Rp and RL. Then the current A prime flowing through the load RL will be given by Rp divided by RL plus Rp times A. If RL goes to 0 here, we get back to the short circuit case, where the current A prime is equal to A. The same, of course, happens if Rp goes to infinity. If Rp goes to infinity, actually, the real current source becomes an ideal current source, A. In general, if RL is much smaller than Rp, then the current I prime will be more or less equal to A. Note that if VL is the voltage across the load and IP is the current flowing through the resistor Rp, then the current A prime can be written as A minus the current IP due to Kirchhoff's law for currents, or A minus IP, which is VL divided by RP by Ohm's law. This result shows that the current A prime flowing through the resistor RL, which is the current provided by the real current source, depends on the voltage across the load and decreases as the voltage across the load increases. Therefore, the model provided for the real current source is capable of reproducing the behavior described by the yellow curve in the plot. The resistor Rp in the real current source is also called the output resistance of the real current source. Based on the results we have obtained, in the case of the real current source, we can say that a current source prefers to work with a short circuit as its load, as in this case the voltage it has to sustain is zero as the power it has to provide. In the case of a short circuit, the output current of a real current source is the same as the current of an ideal current source. On the other hand, a current source doesn't like to work with an open circuit because in that case, the voltage at the output of the current source would go to infinity, and also the power provided by the current source to the load would go to infinity. Up to now, we have been discussing the features of independent circuits, either ideal or real. In the models of active components, like the transistor, or of more complicated circuits, like the amplifier, dependent or control sources are often used. Four kinds of control sources exist. In a voltage-controlled voltage source, the voltage generated by the source depends on the voltage between two nodes in the circuit. The parameter alpha multiplying the voltage VAB has no dimension. In a voltage-controlled current source, the voltage generated by the source depends on the current flowing through a given branch in the circuit. The parameter Rm multiplying the current E has the dimension of a resistance, and is therefore measured in ohm. Voltage-controlled voltage sources are also identified through their acronym, which is VCVS. The same is true for voltage-controlled current sources, which are also called VCCS. In the case of a voltage-controlled current source, the current provided by the source is a function of the voltage between two nodes in the circuit. The parameter Gm multiplying the voltage VAB has the dimension of a conductance and is therefore measured in Siemens. A voltage-controlled current source is also referred to through its acronym, which is VCCS. In the case of a current-controlled current source, the current provided by the source is a function of the current flowing through a given branch in the circuit. The parameter beta in this case will have no dimensions. Current-controlled current sources are also identified through their acronym, which is CCCS. Finally, one important consideration about voltage and current sources of any kind, ideal, real, independent, or dependent. Voltage and current sources provide a very convenient way to model electronic circuits, or part of them, especially when we are analyzing or designing complicated processing chains consisting of the cascade of two or more stages. For example, in this block diagram, we may be asked to design circuit C in such a way that it can properly process the signal coming from circuit B. In order to be able to do that, at least when we start designing circuit C, we may just need to know what kind of signal circuit B provides, whether it is a voltage or a current, and what its output resistance is. This boils down to modeling the circuit with a real voltage or current source. This modeling process can of course take advantage of the Thevenin's and Norton theorems. Voltage and current sources are also used to model the behavior of transducers, devices which can convert physical quantities like temperature and speed, for example, into electrical quantities like voltage and current. As already mentioned, dependent sources are in particular used to model the behavior of active devices and circuits, like transistors and amplifiers.